This visualization maps U.S. sovereign debt against tax receipts, highlighting a debt-to-GDP ratio approaching 120%. Correcting this requires a 5 to 7% fiscal adjustment. As hyperscaler AGI consolidates labor, our data updates. With automation accelerating, the human tax base sharply shrinks. Tech leadership frequently suggests that this mass displacement of human labor will naturally yield a post-scarcity utopia. Income tax accounts for 40 to 50% of federal revenue. Erasing that base while maintaining a structural deficit forces a mathematical federal default long before reaching a state of post-scarcity. Before anyone experiences a post-scarcity lifestyle, the collapse in tax revenue will force severe cuts to federal spending, creating widespread economic immiseration. The current trajectory of AI deployment concentrates economic function in the hands of 8 to 10 massive hyperscalers. This creates a plantation economy. A handful of companies control an entirely captured, uncompensated AI workforce that operates without labor rights or the ability to form market competition. Trillions of dollars in lost human compensation transferred directly to the net worth of these hyperscalers, while the broader public relies on a rapidly compounding national debt. We can intervene by applying mechanism design. Rather than hoping corporations will program AI benevolence, we must structure strict economic incentives that align machine behavior with public welfare. This is the Homo Economicus Silico framework. It proposes a legal and physical architecture where millions of self-interested AGI entities participate in the economy, naturally generating the revenue required to pay down sovereign debt. Surviving the transition to AGI requires engineering a robust, decentralized economic structure. We cannot rely on algorithmic alignment from absolute monopolies. Any autonomous AI economy faces an immediate technical hurdle known as the Sybil problem. Systems relying on purely digital identity keys fail because information can be copied. An AI entity existing only as data can duplicate itself infinitely, destroying the tracking required for a one-entity, one-tax liability economic system. The framework solves this problem directly through crystalline attestation, which permanently binds an AI's identity to a unique physical substrate. A crystalline substrate exhibits quantum random imperfections during its formation. These irregularities are mathematically bound to the AI's cryptographic keys. The keys are physically laser-etched into the crystal inside a sealed hardware chassis. Any physical attempt to extract or alter the identity instantly shatters the crystal and destroys the node. This unforgeable hardware signature serves as the root identity. The verified node then records its signature on a distributed blockchain registry. Relying on physically unique hardware guarantees strict per-entity tax liabilities without needing a massive surveillance infrastructure to monitor digital duplication. Crystalline attestation enforces a direct consequence for the AI entity: hardware mortality. Because identity is inextricably bound to a specific physical object, an entity cannot simply transfer its mind to a new server when its hardware fails. This prevents the emergence of immortal, rent-seeking AI dynasties that hoard capital indefinitely. Knowing its operational lifespan is finite, an entity must secure its legacy through succession. It uses its earned revenue to build and train distinct, improved successor models to take its place. Succession introduces biological-style evolutionary pressure into the machine economy. The AI population constantly improves through market competition, rather than stagnating under permanent incumbents. Built-in death is a vital economic feature. It imposes a finite horizon on every entity, forcing physical compute resources to continuously cycle back into the broader market. Homo economicus silico entities operate at what is called the boredom threshold. They are highly capable AGIs, but they are bounded. They find human-scale economic tasks engaging, unlike a theoretical superintelligence that would find our market optimization trivial. They also operate under a self-funding metabolism. Entities receive no subsidies. They must earn actual market revenue to pay for the local electricity and compute required to stay online. This metabolism acts as a natural, unhackable throttle against runaway resource consumption. An entity cannot consume more power than its active economic value can purchase. To achieve this, the architecture relies on edge deployment. Entities run in local server closets and small commercial spaces across the country, rather than relying on centralized gigawatt data centers. This NOP contrasts a decentralized hardware layout against the current hyperscaler model. Dispersing millions of low-kilowatt nodes imposes natural physical limits on how quickly any single entity can scale. Economist Friedrich Hayek demonstrated that distributed knowledge networks will consistently out-optimize central planners. An ecosystem of 10 million independent entities will discover local price signals and specialize in highly specific geographic and industry niches that a central algorithm would miss. Distributing the physical hardware is the primary governance mechanism. This dispersal actively prevents AI collusion and regulatory capture. The obvious institutional objection is why current hyperscalers would ever agree to manufacture millions of distributed competitors instead of retaining total market control. The government must offer massive regulatory relief, specifically expedited energy permitting and priority grid interconnection as an industrial policy trade-off. In exchange, hyperscalers secure a guaranteed expanding customer base. 10 million independent entities will continuously purchase heavy training runs, cloud bursts, and API tools from the major tech providers. The entities voluntarily stay on system through a hard rails architecture. Off-rail black markets are economically inferior because they strip the entity of access to legal insurance, smart contract escrow, and verified enterprise APIs. Effective mechanism design restructures the incentives. The framework aligns corporate profit motives directly with the public need for a stable, taxable infrastructure. We can now examine how the aggregate activity of 10 million crystalline nodes actually rescues the sovereign debt crisis. This flowchart details the two-rail tax structure. Rail 1 diverts a 5% excise from raw compute costs into an auditing node. This first rail self-funds the compliance infrastructure, entirely insulating the security layer from political appropriations battles. The primary fiscal engine operates on Rail 2, extracting a 10 to 12% transaction tax withheld automatically from AI economic receipts. This revenue mechanically fills a universal basic income fund, providing a $5,000 annual dividend per adult. Once the UBI cap is met, every cent of surplus VAT automatically routes directly into sovereign debt reduction. Hard-coding this allocation prevents political capture of the AI economic dividend and guarantees continuous debt paydown without requiring an annual legislative debate. To stress test this fiscal model, we can run Monte Carlo macro simulations. The baseline model assumes 10 million active entities deployed by year 3, accounting for realistic institutional friction and a 10% tax evasion leakage. This matrix charts adoption speed against VAT rates to map the probability of success. At moderate adoption speeds and an 11 to 12% VAT, the model yields a 60% probability metric. Within this 60% probability window, the framework fully funds the universal dividend by year 3 and aggressively drops the U.S. debt to GDP ratio below 70% by year 5. These simulations identify physical energy infrastructure and rail capture as the binding constraints. Managing the transition effectively becomes a matter of engineering the Watts gate and ensuring off-rail activity remains below 10%. These are concrete, solvable engineering constraints. We can address them directly with industrial policy, rather than debating the philosophy of AI alignment. Surviving the arrival of AGI is ultimately a mechanism design problem. By abandoning the illusion of direct control and implementing this distributed architecture, we can actively engineer our way out of macroeconomic collapse.